Hello, everybody. Thanks for joining. We're recording today another version of a good enough guide to sanitation in the Pacific. This was a training that was delivered at the Water and Wash Futures Conference in February in Brisbane. And we're recording the material again so that it's available online to those who were not able to join us in person in Brisbane. Our trainers today are Mark Allery, who is a local governance and sanitation specialist, myself, Bronwyn Powell, a water and wash specialist working across the Asia Pacific, and Tony Falkland, who's a hydrogeologist with many decades worth of experience across the Pacific Islands. Our learning objectives for our training are firstly to understand the principles underpinning dry and wet biodigestion processes in containment of fecal waste. So we look at aerobic and anaerobic processes. We also are going to present an improved understanding of the principles underpinning the design of septic tanks and soakaways, wet and dry pit latrines, and also we'll take a look at septage and sewage treatment plants, so considering the whole sanitation service chain. The way we've structured the training, we'll start with an introduction. So first of all, looking at the context. We've called this a good enough guide to sanitation in the Pacific. So we will look at what is unique about the Pacific sanitation situation and also the chronic and acute health impacts of poor sanitation. The first section is understanding fecal exposure risks and the pathways as well for fecal exposure, and also take an in-depth look at groundwater safety and setback distances for sanitation, and look at what we know and what we don't know about groundwater velocities and risks associated with pathogen transfer through groundwater. Second topic is around the principles of septic tanks and soakaways, their design, operation, maintenance, and common failings, and also principles of pit latrines, so again, wet and dry systems. And finally, looking at the principles of sewage and septage treatment systems and the different kinds that we find across the Pacific. Thanks. So the introduction is sanitation in the Pacific context. So for those who aren't working in the Pacific, it's good to take a view of the whole picture, which is that even though 1.2 million people gained access to sanitation in the last 20 years, this still did not keep up with population growth. The Pacific lags all regions as far as sanitation access goes. And the greatest lack of service is to rural populations, as you can see on the graph on the right. If we do focus in on urban sanitation, which is what our TA, which is supported by the Asian Development Bank, is looking at primarily, we look at urban sanitation and sanitation in informal settlements primarily. We can see that urban sanitation coverage is poorest in Kiribati, Papua New Guinea, and American Samoa. This is looking at population with basic sanitation, and you can see that the different colours, the highest level, greens, the best coverage, down to very low, as low as 49% in Papua New Guinea. This is again the same similar data presented slightly differently, but also breaks it down at a country level, so you can see access to safely managed, basic, limited and unimproved sanitation, and also the countries that still have some remaining open defecation. You can see from here that only 5 countries are measuring safely managed sanitation. We only have data for safely managed sanitation for those countries that you can see: PNG, Kiribati, Tuvalu, Tonga and Samoa. Thanks, Mark. Could you keep clicking, please? There's a few descriptors. Yeah. So this diagram, I should acknowledge Mark Ellery put this together, from JMP data, and it identifies the main types of fecal sludge management that exists in each of the countries in the Pacific Island countries. So we can see up the top the ones with the greatest percentage of septic tank coverage: Tonga, Samoa, Vanuatu, and then down the bottom those that have greatest percentage access to sewage systems, so Tuvalu, Palau, some of the atoll countries. We're not sure how accurate some of this data is. There is from our workshop that we just ran, there's in fact, terms used such as Pacific septic, and it's possible that some of the data may not be as accurate as we'd hope, particularly, for example, that percentage of 81% access to sewage sanitation Tuvalu is not consistent with what we would guess it to be. So this is the best we have, but we still question how accurate it is. Thanks. We will today look at all aspects of the sanitation service chain, the way, you could keep clicking, I think there's more to these diagrams, the way that on-site sanitation is managed through either like nose transport off-site, or whether it's transported and disposed off-site. So we can see there the on-site sanitation pit latrine, the septic tank, those that are discharged and just treated on-site, and those that are moved off-site. So I think the next slide we move on to is Tony. Thanks, Tony.
Thank you, Bronwyn, and hello, everyone. So I'll be taking you through a few slides to look at what is unique or special to the Pacific Islands. And one thing that stands out is the large diversity across the Pacific Islands. This covers the physical nature of islands in terms of their size, shape, elevation, geology, and other factors. And these would be climate, especially the rainfall, which is very variable in space and time. The variation in hydrology, which includes hydrogeology, is also very variable, which affects the water resource availability on these islands. And other factors such as demography, culture, and the degree of economic development and the degree of isolation also show a large diversity. In terms of the last item there, one aspect of that is that many islands in the Pacific are only reached by boat. Moving on to the physical characteristics of Pacific Island countries, we're looking at the 14 actual countries and not territories of other larger nations. And in the second column there, you can see the large variation in total land area measured in square kilometres, from 21 for Nauru, 26 for the islands of Tuvalu, right up to over 460,000 square kilometres for Papua New Guinea. In the third column, the number of islands or atolls vary from 1 in the case of Nauru and Niue, up to more than 600 for the Federated States of Micronesia, close to that for Papua New Guinea, and even approximately 1,000 for the Solomons. In terms of island type, there's quite a variety there too, which you can see in the fourth column. They vary from volcanic to limestone to atolls, and those with mixed geology. And in this slide here, there are a number of diagrams that show variations in the types of geology, from volcanic islands that are still erupting to ones where fringing reefs have formed, through to atolls where the volcanic structure is below sea level, and to islands which are limestone above sea level with volcanic structures below. And there's quite a few other types which are shown in these 9 diagrams. Populations shows quite variation too, both in terms of numbers. Second column here, about 1,500 people in Niue, up to about 9.3 million in Papua New Guinea. The densities in terms of people per square kilometre over the whole country shows large variation too, from 6 in Niue up to more than 500 in Nauru. Growth rates, there are large ones in the Melanesian countries, shown here in green, and to even negative growth rates in some of the smaller islands, Marshall Islands, Niue, and Tonga. All of this data comes from the Pacific Community website. Urban populations also show, and rural populations show, marked changes in the percentage of both, from 100% in Nauru down to 13% urban in Papua New Guinea. In terms of a single island or atoll, it's interesting to look at, say, Tarawa, and within an individual island such as Eso, which is at the western end of South Tarawa, the population densities can get as high as 12,000 people per square kilometre, whereas in rural area of Tarawa, it's much less. The geology has an influence on the groundwater resources, and we're mainly dealing with groundwater resources here because it's sanitation that largely affects groundwater resources. We can divide types of groundwater resources into two types of aquifers, namely a perched aquifer system and basal aquifers. The perched, the more common type, is depicted here. It's more of a horizontal aquifer, but you can also get vertical ones which are confined behind volcanic elements called dikes. These do occur in some of the islands in the Pacific. In terms of the basal aquifers, you have coastal aquifers which occur around many of the high islands, where basal aquifers are in contact with underlying seawater. And apart from the coastal aquifers, we have what are called freshwater lenses, which occur as freshwater bodies on small coral islands, and underlying the freshwater zone is transition zone and seawater. Now, the scale of vertical and horizontal here is quite exaggerated. This slide sort of shows a more realistic thickness of the freshwater zone compared to the width of the island. The freshwater zone could be anywhere between about 2 metres and, say, 15 metres, and a brackish zone could be around about similar, 15 metres, and underlying that is seawater. This slide just shows a cross-section through an island such as Nauru, with the limestone capping is on top of a volcanic structure, and on the very top of the island above sea level we have limestone below, a very thin freshwater zone in some parts of the island. This one shows mean annual rainfall at sea level across the Pacific, which can vary at sea level, obviously, from as low as about 700 millimetres in the eastern Pacific to 5,000 millimetres in the west. In the mountainous areas of some islands, such as Papua New Guinea, but also in some of the high islands in Federated States of Micronesia, the rainfall can get close to 10,000 millimetres. So spatially, there's a large variation. Also, in terms of temporal variability or over time, there's a high degree of variability in some islands, and this example is one from Kiribati for the island of Christmas, where the histogram here shows the variation over 100 years, and key features are that the average is about 920 millimetres, but the highest annual is approximately 3,700, and the lowest is about 180. And these highs and lows are largely influenced by El Nino and La Nina episodes. And one interesting feature is that over the period of 100 years, the rainfall has trended upwards, but with a large amount of variation. And the equation here shows that there's approximately a 5 millimetre increase on average over that 100-year period.
Thanks, Tony. It's great to get a good understanding of the geology and the different contexts with different kinds of islands we're dealing with in the Pacific and their hydrogeology. Fantastic background for everyone. So moving back into sanitation, for those who are already working in on-site sanitation, you're probably familiar with what we call the Green Book, the WHO Guidelines on Sanitation and Health. So this is what the Green Book says safely managed sanitation should look like. So from containment, the toilet or the interface, through conveyance, treatment and end-use disposal. And we see here on-site sanitation systems, so dry and low flush, then on-site sanitation systems requiring faecal sludge management and off-site treatment, such as septic tanks, and then also conventional sewage with off-site treatment. Sorry, can you click back again one, Mark? So the first diagram along there you'll see is an alternating twin offset pit latrine. We actually do not see any of those yet in the Pacific. If you click forward one, what we do see more is quite a lot of direct pits. In this case, it's showing that the best safe disposal would be just closing it off and planting a tree. So if we keep going, that's what safe sanitation should look like. But in reality, what we see is all kinds of variations of that and not safely managed sanitation in many instances. So we see pit latrines that are not well sealed. We see septic tanks that are discharged direct to the surface. We see waste treatment plants where sludge is extracted before it's properly treated. And that bottom picture is just effluent pond, basically. It's not being treated properly at a package plant. So if we move to the next slide, some of these common problems are captured on this slide for the different types of sanitation systems. So particularly for on-site sanitation systems in the Pacific, we see a lot of do-it-yourself designs made out of local materials or what people have available. We see that there's often overflow to the surface. They can be poorly managed, and then people have problem with odours and those kinds of things. In terms of conveyance, pits are very rarely emptied, and if they are, there's a lack of safe treatment and lack of facilities to dispose or to properly treat fecal waste. That's a similar story with septic tanks. There are some exceptions in the Pacific. Shouldn't paint everything with the same brush, but there are a lot of challenges across service chain, both for septic tanks and, as we'll see, for sewage and conventional sewage. There are sometimes kind of higher and more concentrated risks if these systems break down. So I think next slide, thanks. So you can see that there's already quite a bit that's unique about sanitation in the Pacific. The principles that we'll share and Mark will mostly speak to in this training, many of them are universal, but there are particular challenges set by the Pacific context, the geography and hydrogeology, as Tony's already discussed. Also, we can see in the terms of context, there are those areas that are atolls, high population densities, and also peri-urban areas where land access and a whole range of lack of market issues make sanitation provision very challenging. The culture and history of sanitation in the Pacific also poses a bit of a challenge for practitioners. Sanitation itself is often taboo. People really don't want to talk about it. Sometimes when we've tried to guide, I've had group discussions in conferences and whatnot about sanitation, the conversation will quickly go to solid waste. So there is a kind of aversion still in many places to talking about sanitation. There are also, in many places, very complicated cultural and gendered beliefs around siting and use of sanitation facilities, which means that consultation and inclusion in planning of any facilities is critical. And also making sure that it's gender-sensitive approach is taken in designing these systems and building these systems. There is also a bit of a history of handouts. Sorry, back again. Thanks, Mark. Still going on that one. And in terms of people being given a toilet, so there hasn't been a great deal of focus on demand creation in some settings. In terms of sustainability, we see operation and maintenance under-supported, under-resourced in many places. There are very few safe disposal options, and there are capacity constraints where there are disposal options. Next, thanks. So we've tried to capture what we think are some of the common misunderstandings about sanitation in the Pacific, and when Mark presents, we'll go through and show why this is a misunderstanding and then present a lesson about what is really the better way of thinking about this issue, and that will come right at the end. So if we just go through these, the first one there is that of a common misunderstanding that fecal contamination of groundwater sources is primarily through the groundwater. So Mark will show that surface contamination is also very likely and more common probably. Though we will also show there's many unknowns and areas that still need research for on-site sanitation. The second misunderstanding there, that septic tanks significantly reduce pathogens in fecal sludge and effluent. Third, septic tanks with soakaways are always superior to on-site option. We see this as a common push, that people want to move to a septic and don't think of on-site cesspits as viable or good options. Fourth, that there's no problem operating dry pits as wet pits. And fifth, that mechanical sewage treatment plants always reduce fecal exposure risks. Thanks, that's it from me, I think, and over to Mark now on the first topic of the soil is our friend.
Thanks, Bronwyn. Thanks, Tony. The first common misunderstanding is the role that the soil plays in the attenuation of pathogens, and we're going to run through a bit of background, Tony and I, to try and kind of set the context before we drop down into looking at the various technology options. The Good Enough Guide is broken into basically 4 components. This first one is really around understanding the origins of fecal exposure risks, and then we will look at septic tanks and soakaways, pit toilets, and sewage treatment systems in that order. The Good Enough Guide doesn't seek to replace the instruments that already exist, technology manuals, local government acts, planning codes, environmental regulations. The Good Enough Guide seeks to supplement these with principles underpinning the trade-offs that enable practitioners to choose sensible options within what is, we think, a very complex context. While we're quite aware of the acute consequences of exposure, fecal exposure, in terms of sickness, loss of weight, increased incidence of child wasting, epidemics, greater risk of child mortality that are borne as costs to households and the public health system, we are less aware of the chronic implications of constant exposure, fecal exposure, that manifest as infections in the gut, leading to a failure to absorb nutrients, and the micronutrients or the tablets or the antibiotics designed to mitigate those problems in the first place, that lead to an increased incidence of low mother weight, low child birth weight, an increased incidence of child stunting, that are born as a failure of children and adults to reach their intellectual and physical potential, that exacerbated or are kind of witnessed as a failure of countries to achieve their economic potential. We know from while the exact correlation between sanitation and stunting is not well defined, we do know that there is a very strong correlation between open defecation density and stunting. And so while the data doesn't show strong correlations between sanitation and stunting, nor does it show strong correlations between open defecation and stunting, what the data does show is a strong correlation between the density of open defecators within a particular area and the incidence of stunting. And so this is essentially a proxy indicator of the exposure to fecal exposure. While children may be shorter, what we do see is that over time, this change is reflected in the height of adults. And so the Dutch were not always the tallest people in the world. Back in the 1800s, the Germans and the British were actually significantly taller than the Dutch. And what we see is that the inflection points in these in the changes in height of people over time are related to the introduction of sanitation systems. So what we're seeing here is the implications of reductions of chronic exposure in the height of men over time, and the previous slide in the incidence of stunting in children. The exposure to fecal waste and the reduction of the pathogens that affect growth in children and in adults naturally occurs through either aerobic or anaerobic processes. And probably the most important 2 points to take away is that aerobic digestion systems, or digestion of fecal waste with air, is much more efficient in reducing the pathogens, whereas anaerobic processes are much more efficient in reducing the volume of fecal waste. A corollary of this is that aerobic processes can really only work in solids once the solids are dry, so that the air can enter into it. So aerobic sludge that is wet is very difficult for the neutralization of the pathogens, whereas dry sludge enables aerobic processes much more readily. The inverse is also true, that with liquids that have lots of solids floating in them, it's very difficult for the aerobic processes to enter in to neutralize the pathogens, because the pathogens will hide in the floaties in the liquid. However, if the liquid is clear, it's quite easy for the aerobic processes to enter the liquid to neutralize the pathogens. And this becomes quite important when we look at our setback distances and what's happening in the soil. So the WHO back in the 1980s defined this minimum safe distance between a pit and a water source as 2 meters vertically, or 2 meters in unsaturated soil. But where does this 2 meters come from? And the first assumption for this 2 meters setback is that there is establishment of a biofilm, or a icky, gooey biological film established where the effluent particles, or the fecal waste particles, establish an anaerobic zone, and where this biofilm of very thin faecal deposits establishes. The biofilm over the course of the first month will establish and is incredibly efficient at attenuating pathogens. While it slows down how fast the liquid will penetrate into the soil, it does facilitate an extremely efficient set of biological processes for neutralizing pathogens. The first of the pathogens to be neutralized will be, or to be attenuated, will be the parasites, the protozoa and helminths. And they are pretty much all retained within about the first 300 millimeters, although they can last a very long time, up to about 1 year in the Pacific. They're not going anywhere. They're going to actually stay quite close to the pit. The second, within about the next 300 millimeters, directly below the biofilm, there will be aerobic zone will be established, in which aerobic bacteria, aerobic organisms will hunt fecal bacteria and will tend to attenuate all of them within about the next 300 millimeters. The viruses are the smallest and the most mobile and the most likely to travel below the pits. But within about the next 300 millimeters, most of the, or 4 log of those viruses will be attenuated within that 900 millimeters or a meter below the bottom of the pit. While the viruses can last up to 20 days in a wet condition, here, as we do have a dryish zone that's established underneath the biofilm, and so their survival time will be significantly less than those 20 days. The survival time of pathogens in the Pacific, we have quite conducive situation for the reduction of pathogen survival lives. We have higher temperatures, we have drier soils. If we are putting our pits closer to the surface, and if there's not a lot of competition for other nutrients, we have a very favorable environment for the reduction of the survival time of pathogens below what's listed in that table there. Similarly, the migration, the likelihood of pathogens moving decreases in conditions that we might typically find in the Pacific, a saline environment, drier, unsaturated soil, finer soil, and the final point is at lower hydraulic loading rates. So not overloading the pits is conducive to attenuate the non-migration of pathogens. While the design criteria suggest less than 50 millimeters per day, the data suggests that there is quite a bit of space or room for movement before we reach the breakthrough pathogen loadings. Finally, soakaways, while soakaways are reasonably effective at attenuating phosphorus, nitrogen is really the nutrient that is most likely to get through, and however, nitrogen is not so much of a health risk as it is an environmental risk. The other kind of condition that we're concerned about is what happens is the horizontal distance between a soakaway and a water source. And this is quite a different condition. This is a condition where the pit is in the water. So rather than having a distance above the, like relying on our vertical setback distance. Here we actually have the pit in the water and the water flowing from left to right here. And so what is that setback distance? The WHO has defined a guideline value of 15 meters. But again, where did this 15 meters come from? The 15 meters assumes, again, the establishment of a biofilm around the soakaway or the pits. And I imagine that this soakaway will kind of move a little bit in the direction of flow, but its existence on the upstream side of the pit in some ways protects the pit and from the flow sweeping through the pit and trying to mobilize the pathogens within the pit into the groundwater. The parasites will be the first to be attenuated, primarily even before the biofilm. Data on transit times for bacteria suggests that they will last between 4 to 7 days in the water. 4 days in aerobic conditions in the water and 7 days in anaerobic water. By and large, in the Pacific, our water will be, because it's kind of predominantly either come through rainwater or through limestone, as Tony indicated, some kind of limestone sediments, there will be oxygen within that water most of the time. And so we would expect in most cases, we would be looking at bacteria survival transit times of around 4 days. And therefore we can assume that the 15 minimum safe distance of 15 meters, knowing that the velocity for the setting for this was about 1.5 meters per day, that it's based on a transit survival time of about 10 days. And so we can reasonably safely assume that our virus transit survival time within the Pacific is going to be 10 days at a maximum and probably considerably less. We also are interested in this horizontal velocity because the WHO assumptions are based on the hydraulic gradient being primarily topographical here, whereas in the Pacific, our likely influences on the lateral velocity are going to be anthropogenic or tidal. And the groundwater velocity may be, while the assumption for the WHO guidelines is that the groundwater velocity is horizontal, we would probably expect in our setting that it's likely to be vertical. But these are questions of hydrogeology, and I would request Tony to help us out a little bit here with a couple of these questions around what's likely to be occurring in the groundwater in the Pacific. Thanks, Tony.
Thank you, Mac, and we'll see what we can do. We'll be looking at groundwater profiles and velocities in the Pacific, taking a specific example of the island of Bonriki, which is on Tarawa Atoll in Kiribati, as described in the earlier session. Bonriki and nearby Boita Island, they're the main current sources of fresh groundwater for South Tarawa. And groundwater is pumped from the freshwater lenses on these islands using what are called infiltration galleries. The groundwater is also extracted from village wells on the edge of both of these islands. This is an aerial photo of Bonriki Island with the ocean up in the top of the screen and the lagoon down here at the bottom. We have some village areas marked in red outline around the edge of the island. It also has the main international airstrip. And within this middle area, there's fresh groundwater, which is pumped using these infiltration galleries. One note is that village areas on the edge of the island have on-site sanitation. This slide gives an idea of the type of pump station from the outside. This is inside. The groundwater is about 2 meters below the surface of the ground. And then about 1 meter below the water level, there's a series of horizontally laid slotted PVC pipes, which enable the water to be drawn in through the slots and then pumped, where it combines with other water from galleries and then is distributed down South Tarawa. We're going to look at a cross-section across Bonriki on this line, where the distance from lagoon to ocean is about 900 meters, and the maximum height of groundwater above mean sea level has been measured around about 0.8 of a meter at about 400 meters in from the lagoon side. So if we look at the cross-section, we're saying that the maximum groundwater level is about 0.8 of a meter above mean sea level. It does move up and down with the tide by about 100 millimeters or so. But this 0.8 of a meter shows us the height above mean sea level. Now, the diagram shows a slightly thicker freshwater zone towards the lagoon side. That's largely because of the sediments, which are finer on the lagoon side than the coarse sediments on the ocean side. And water, once it reaches the island, could travel downwards or horizontally, and we'll be looking at that. In this slide, we're going to do a couple of calculations of velocities. The first one is to calculate an average horizontal velocity from near the center of the freshwater lens to the edge of the island, using this equation here, which Mark showed in one of his slides, where the horizontal velocity is equal to the hydraulic conductivity multiplied by the hydraulic gradient, which we can work out from the height of the groundwater above mean sea level divided by the distance from the lagoon, and divided by a term called effective porosity, which is the portion of the total void space in a porous material, in this case an aquifer, such as a freshwater lens, that can transmit fluid. And from measurements, the hydraulic conductivity is 5 meters per day on average. The hydraulic gradient calculated as that value, 0.002, and effective porosity for this sort of sandy, gravelly aquifer is about 0.3. If you work out from the formula above, it works out to be about 33 millimeters per day. Now, using this velocity and the distance traveled in 10 days, which, as Mark pointed out, is a probable virus transit survival time, is about 0.3 of a meter. The time taken to travel 15 meters, which is known as the minimum safe distance before, calculated at about 1.2 years. And for a molecule of water to get to the edge of the island, the 400 meters, could take 30 years or more. So at the long time for horizontal velocity to reach the edge of the island. Now, in terms of vertical velocity, from the surface of the freshwater lens to the base, the velocity is equal to the groundwater recharge rate. And the recharge rate has been calculated as about 40% or 0.4 of the average annual rainfall based on previous studies, which then means the average recharge using 2000 millimeters average rainfall is calculated about 800 millimeters per year, and that works out to be about 2.2 millimeters per day. And hence the vertical velocity is about 2.2 millimeters per day. So you can see there's quite a difference between the two, but the results using this velocity, the time taken to reach the base of the freshwater lens with average thickness of about 10 meters and an effective porosity of about 0.3 is approximately 4 years. Hence, molecular water is more likely to mix with the saline water in a vertical direction below the freshwater zone than it is to move sideways to meet the ocean at the edge of the island. And just to finish off, we'd like to look at the influences on groundwater level on a small coral island. Firstly, the natural influences due to sea level movements, mainly tides, is around about 100 to 150 millimeters, which happens twice daily with highs and lows, and that's approximately 5 to 10% of sea level movements. Due to short-term extreme rainfall, which could be up to about 150 to 200 millimeters per day, the groundwater level could move up to 1 meter, and this influence could occur over several days before it resumes its equilibrium level before the rainfall started. And due to the longer-term rainfall changes from El Nino, La Nina cycles, that movement of the groundwater level could be in the order of 300 to 500 millimeters, and that influences over several years. So we now move on to anthropogenic influences. The drawdown due to pumping from infiltration galleries, such as in this water reserve, have been measured at only 10 to 50 millimeters. The pumping is generally continuous, and as you can see from the values here, it's minor compared with other influences. But drawdown due to pumping from wells, for instance, in the village areas, maybe not so much on Bonriki, but in other islands, it's variable, but it could be up to about 500 millimeters or half a meter. Generally intermittent, but it can be significant in terms of its influence, depending on the capacity of the pump. And to finish off with just a brief comment on the types of extraction facilities on small coral islands, but also in coastal zones of high islands. If we look at dug wells, groundwater drawdown can cause movement of contaminants towards the well and seawater intrusion from below. The movement sideways would be dependent on the amount of the drawdown due to a pump. Boreholes, such as this one over here, can cause significant seawater intrusion and are certainly not recommended for small coral islands. Infiltration galleries, such as the ones at Bonriki, cause very small groundwater drawdowns and hence have insignificant impact on the movement of contaminants and seawater intrusion. And with that, I'll be handing back to Mark. Thank you.
Thanks, Tony. The final, and just to conclude this session is basically just with the to debunk the misunderstanding, if you like, that fecal contamination of groundwater sources occurs through the groundwater. And what this study from Bangladesh shows is that only 1% of the risk to drinking water sources actually occurred through the groundwater. 99% was through surface contamination. This study from Bangladesh was extremely interesting. It looked at really the worst case scenario of toilets sitting in the ground under tidal influence, and what conclusion it came to was that outside of this radius of 2 meters, which they called the near field groundwater range, that the risk to water sources was actually extremely low, and it was in the range of 1 to 10 coliform forming units of fecal coliforms per 100 mil 5% of the time. And I kind of imagine this 5% of the time being probably at spring tides, when the tide basically carries a packet of pathogens over the top of our biofilm. And when you get these kind of small packets of pathogens that get around the biofilm and make their way to the water sources. But the big lesson learned here is that just because we're seeing contamination of groundwater sources doesn't mean that the contamination is coming through the ground. There's a high likelihood, and we think especially in the Pacific, that the contamination route for the contamination of the source is over the top, not down through the bottom. We still, like the thinking around this, we still have a lot of questions, and we're still working and looking for engagement with others in terms of actually looking at what are the lateral groundwater velocities in these different settings, what's the probable survival time of pathogens, and what happens to the biofilm in different settings, and potentially even with the introduction of chemicals or the use of bleach or on septic tanks or pits, and how does that affect the operation of the biofilm. The next topic we would like to cover is really just getting into the technology options now. And so the next one is looking at septic tanks and soakaways, and really reinforcing that the septic tank is not the hero here. The soakaway is the hero of this system. We're going to, and again, really the septic tanks and soakaways, by and large, often are captured in building codes and in urban settings, often in the Pacific. We find them less in rural areas. We find them more in urban, often where there's access to trucks, for septic tanker trucks for the disposal, emptying, transport, treatment of the waste. The first point we would like to make here is that septic tanks don't reduce your pathogens. The septic tanks are really a device for separating out your solids from your liquids. And this clever T-piece here reduces the likelihood of fats and scum entering into the soakaway. It enables the liquid to be drawn from the bottom and your methane gas to be drawn from the top and into the soakaway. And as we've already covered, most of your pathogen and phosphorus reduction will occur beneath the biofilm in that aerobic zone below the soakaway. And the one thing that will get through, the one thing that will get through is nitrogen. However, there are opportunities to design for the uptake of nitrogen, either in plants or in the presence of carbon in anoxic soil. The effluent bypassing a soakaway or removed from the septic tank is extremely dangerous. It will still have excessive pathogens and nutrient levels. It really needs the soakaway, and passing through the biofilm is really the key for the reduction of pathogens within effluent leaving a septic tank. Methane released through a soakaway will be converted into CO2, and we're still one area of research is looking at the efficiency of this in lowering overall greenhouse gas emissions. But we do know that CO2 has a significantly lower footprint than methane, and therefore the conversion of methane to CO2 in the soakaway reduces the overall carbon loading from septic tanks and soakaways. Sludge will accumulate in the septic tank and will need to be pumped out from time to time. However, it's worth noting that this is still very liquid. It will be in the vicinity of 96 to 98% liquid, so 2 to 4% solids. It will have high pathogens, but you will see here it's also got concentrated nitrogen levels. So the design of septage disposal facilities needs to understand that you are getting elevated levels of nitrogen in your septic sludge. Sizing of septic tanks are based on a effluent attenuation time or retention time within the tank of 24 hours. Now, that's 24 hours when the sludge is at the point that you're ready to remove it. So in terms of sizing a septic tank, we need to size it based on how much sludge will be in it, how long will it take to fill up with sludge and still have 24-hour retention time for the liquid. Of course, the more liquid, the bigger that's flowing through per day, the bigger that area has to be. So it ends up being quite a kind of complex calculation based on retaining a 24-hour retention time for the liquid, how much sludge, and then allowing for a freeboard. Based on the Australian standards, if we of 50 litres per capita per day for black water and 150 litres per capita per day for black water plus grey water, assuming the Australian standard assumes 98% moisture content, which gives us roughly 50 litres per capita per year accumulation of sludge, and 80 if we're putting in grey sludge as well, because black faecal sludge is about 50 litres per person per year. But if you've got grey water, you've also got fat and skin, and you've got a bit of food waste coming in. So the sludge accumulation rate is greater. So we need to allow for a greater accumulation if it's black plus grey. And that will give us our rate of accumulation of 3 to 5 years. If we assume a reduced density, it basically would double that sludge accumulation rate, and which is the point at which it should be emptied. Noting here that septic tanks should be emptied before they fill up, when you still have a 24-hour retention time, not once they fill up. And that's often requires a bit of testing, measuring of your sludge layer in a tank using a dipstick, or trying to actually understand what the level is before, at the point when you empty the tank. Why is this important? And knowing how long a tank should take to empty, and the sludge generations of households. One of the things we can do very quickly and easily is to use the number of trucks in a city as a proxy for understanding what's happening with our fecal waste. A couple of examples here. If you look at Honiara City, we know that they have roughly 11 septage trucks in operation. But if we look at the sludge generation rates and the various technology options, and how much fecal waste people of the city would generate, we can come to the conclusion that the city really only needs one truck to handle the volume of fecal waste that would be generated in the city. The extra 10 trucks leads us to presume that a lot of these tanks are getting emptied, are filling up with water rather than sludge. And so that these trucks are being engaged to transport water rather than transport sludge. The inverse is true for a city like Dhaka, where if you crunch the numbers similarly, you see that Dhaka city would need over 100 trucks just to transport the amount of fecal waste that should be generated from on-site systems. But we know that Dhaka city has less than 2 trucks. And that means that most of the fecal waste is actually being removed and transported either informally, or it's all just going into the stormwater drains. And it is a combination of the two, but by and large, we know that the septage is basically just finding its way into the stormwater system rather than into the to treatment systems. So knowing sludge accumulation rates and sizes enables us to actually backcast and do some analysis of what's happening in these various cities or settings. Which leads us to the importance of the soakaway, and that the soakaway, what we see in these situations, and both of these case studies actually result from failures in soakaway designs, leading to actually other mitigation options. And so getting the design of the soakaway right is probably the most important part of septic tank designs, because if you get that wrong, it surcharges into the septic tank and it fills the septic tank prematurely. There's 2 ways for designing soakaways in practice. The Australian standards rely on the design based on the infiltration zone only. So they're really just looking at the bottom area underneath a septic tank, underneath the soakaway or underneath the soak pit. This results in extremely long trenches or lots of pits because they don't make any allowance for sidewalls. And what we realise is that the sidewall is quite an important means of percolation or release of effluent through soakaways. The British standards do the opposite. The British standard look really just only on the sidewalls, and they look at they design based on the sidewall only, which results in much shorter trenches and fewer numbers of soakage pits. But often they have this design criteria of a design loading rate of 50 millimeters per day that ends up defining the sizing of most soakaways, because that's that's the point at which the sidewall calculations become irrelevant and they just use this bottom design loading rate. In the Pacific, we probably can look at where in settings where risks to groundwater are minimal, where the population drinking the groundwater is low, we can actually come up with guidelines around the sizing of soakaways. And so we think that you could potentially size soakaways based on 1 metre per person, based on the Australian standards of 0.4 by wide by 0.4 metres deep, which will prevent the surcharging of effluent to surface. for black water only. If it's black water plus grey water, the length should probably be tripled. Proximate to drinking water sources, the length should probably be halved. And if the in gravelly sand, you could probably halve the length of this pit. So it could be 0.5 meters of soak away per black water only user. Still, the sizing of soakaways, even as per the Australian standards or the British standards, it's still an attempt to estimate where the biofilm is and to calculate based on the volume of flow through the biofilm. As a result, there are still lots of unknowns around the sizing of soakaways and areas where we would like to engage further in terms of actually understanding what's going on in the sizing of soakaways. There are also opportunities for optimizing soakaway sizing based on the separating of black water from grey water, which we know is quite common in the plumbing in the Pacific. But what that means in terms of soakaway sizing, we're still trying to learn there. And then the reduction of methane gases and attenuation, the use of vent pipes, other questions that we're still working on and still trying to understand further and looking for collaboration on. Thank you. The next topic is on pit toilets, and really knowing the importance of aerobic processes. We're really trying to, in the principles of pit toilets, really would like to know where are these aerobic processes occurring. Pit toilets really relate often to informal settings and rural settings. And we'd like to just run through the principles of pit toilets and unpick the difference. Pit toilets are not the same. And we'd like to kind of separate this strongly into the two typologies of pit toilets. Pit toilets can be divided into basically anaerobic and aerobic toilets. One whose functionality fails without water. Anaerobic toilets need water, and dry pit toilets their functionality fails with water. And so water becomes really the key distinguishing, and exposure to water becomes the key distinguishing factor between these two types of toilets that essentially look quite similar, but are deeply different in the way they function. Firstly, functionality in regards to anal cleansing choices. Wet pit toilets or water-sealed toilets, you can use water for anal cleansing or toilet paper. Other forms of anal cleansing materials cannot go into the toilet, and so they need to be dealt with differently. Dry pit toilets, on the other hand, any form of anal cleansing materials is permitted, really, except for water. Within the environment, anaerobic or wet pit toilets can work underwater, can work in water, and are quite able to be quite versatile in terms of the exposure to high water table settings and even inundation. Whereas dry pit toilets will be destroyed, and potentially even when water enters the toilet, they create a very high risk of emptying the contents to surface. In terms of what happens when they fill up, again, completely different. You know, wet pit toilets can be pumped out, but the contents will never be safe. They need to be transported safely and disposed of safely. Aerobic toilets, on the other hand, they can't be pumped out. You can't pump out a solid, but if they're dry, they can be dug out and can be turned into the soil. And so really, you know, like the managing of moisture is the key for water sealed toilets, and minimizing moisture is the key for dry pit toilets. And just to run through the implications of that, in terms of, you know, the wet pit toilets, there's a whole range of factors that affect how quickly they will fill up in terms of how much grey water and black water they receive, and similarly for dry pit toilets. The loading rates at the bottom look quite similar, but as we've kind of indicated, not only are their operating characteristics extremely different, but the sludge at the bottom in dry pit is of a very different consistency between these two settings. So for dry pit toilets, the key for optimizing dry pit toilets is to minimize the moisture and reduce the risks of ingress of water into the toilet. What will happen when water comes in, it kills the aerobic bacteria will be destroyed, and you will get the awful smell of the dead and decaying bacteria when it switches from an anaerobic state to an aerobic state, and vice versa. The maximizing airflow, and there are multiple ways that you can maximize airflow, but putting a cover on the pit is actually is like closing the vent on a chimney. It reduces the airflow and it inhibits the formation or the establishment of the aerobic bacteria and aerobic processes. Managing of odors can be done through the addition of things like wood chips or lime or ash or dry leaves or seashell, crushed shells. And reducing urine is potentially a critical strategy for optimizing the operation of the pit and reducing the generation of odors also from the concrete. For dry pit toilets, the key is to know that the pit needs to be moved when full. Either you need to move it to empty it, or you need to move it and dig a new pit, because it can't be pumped out. In some cases, you can pump them out by turning them into a muddy entering water, but then you enter into this whole realm of having to actually then wait for the state to change from anaerobic back to aerobic as you bring it back into operation again. Wet pit toilets. A wet pit toilet is effectively a combined septic and soakaway all in one simple little pit. So you essentially have your septic on the inside and your soakaway is the soil around the outside. Most important here is that the pit is not sealed on the sides. We need it venting into allowing the methane to vent through the side, as well as the liquid to vent through the side. The bottom will clog and we'll get that nice biofilm starting to form up and around the pit on the bottom. Cesspits can't handle grease, because if you can imagine the level going up and down inside a cesspit, and if the grease is sitting on the top of your water level, it will seal your pit and it will inhibit the liquid flowing through the sidewalls into the soil. If cesspits fill up prematurely, we can actually accommodate that by placing rocks around our chamber, whether our chamber is made up of, whether it's a 44-gallon drum with holes in the side, or whether it's tires with spaces in between. By placing rocks around the outside of that, you can increase your effluent absorption area. And so we're effectively creating a soakaway that's much bigger than our storage pit. And it's a cheap way of expanding our pit if it fills up too quickly with liquid rather than with sludge. Another option is to put a pipe in out of our first cesspit and have a second one in series. This increases our volume of storage as well as increasing our effluent absorption area. When cesspits fill up, one option is to actually take that one offline and bring a second one online. This enables the aerobic bacteria to enter into the pit and to neutralize the pathogens. And so we're able then to dig out that second pit safely. And it's recommended that you then bury that or turn that into the soil. But you see, again, it's the introduction of the aerobic bacteria here into a pit once it's taken offline that really, and the drying of the sludge that enables the pathogens to be neutralized in that offline pit. Finally, one of the advantages of cesspits is that they run at much higher densities than septic tanks. And so therefore, the good design and getting the right design of your effluent absorption area will enable these cesspits to run at much higher sludge densities, so they will fill much slower than a septic tank. And therefore, not only are they cheaper to install than a septic tank, but they're cheaper to maintain than a septic tank. Which brings us to this kind of misunderstanding, that septic tanks are always superior to cesspits. And what we've seen here, is that in certain settings, cesspits offer a low cost and a low capital cost and a low O&M cost as compared to septic tanks, as long as and they also offer a low emptying option, or an option where if you don't have tanker trucks, how you can manage your sludge. But they can't accommodate fats and grease. They also don't offer an option for addressing nitrogen if you want to do that in between your septic and your soakaway, if you want to actually introduce some nitrogen removal system in between. And so there are occasions when cesspits are superior to septic tanks. The other misunderstanding, and we observe a lot of dry pit toilets being operated in a wet state. And so you can do it. You can operate dry pit toilets as in a wet pit state. But there are several disadvantages of doing that. And they carry much higher greenhouse gas emissions. They also smell a lot more every time they switch state between being anaerobic and aerobic. And if you can run a dry pit toilet in a wet state, there's no reason why you can't just put a water seal here and make it a conventional water seal toilet running properly in an anaerobic condition and venting your methane through the sidewalls into the soil, and with a water seal that prevents tidal or influence of emptying the contents to surface. So you can do it, but it's generally, it's not okay, and I think we can do better. There's still a lot of kind of questions, and effectively, we still have a lot of questions around sludge densities in toilets, but we're looking to try to continue to explore these questions and for partnerships around these questions surrounding the optimizing of dry pits and wet pit toilets. The final topic is on when we're in the Pacific, we see, once the sludge is removed from the cesspit or from a septic tank, it needs to be treated in a septage treatment plant, or we see in some places package plants being introduced in high-risk settings, or where there's capacity or pressure to actually go for higher technology options. And so we think it's worth just quickly covering a couple of these principles of septage and sewage treatment plants. We're going to look at on-site treatment plants and then quickly cover a couple of the behaviours associated with network sewage systems. Firstly, septage treatment plants. And really the key thing driving the choice of septage disposal plants is the management of nutrient risks. As we see, the soil is quite good at dealing with pathogen risks, and the selection of sites for septage treatment plants, you can basically site them somewhere where you can design in the attenuation of your pathogens. The first option is basically just a hole in the ground. And when you design a septage treatment plant that is basically a hole in the ground, you're going to attenuate your pathogens and your phosphorus, but nitrogen will leach through and you are comfortable with the risks to environment from the concentrations of nitrogen through the bottom of the pit. The second is kind of design is where you want to concentrate the nitrogen in the sludge. And this is where you will actually design lined pits, and you'll line the pits and allow for overflow of effluent into a soakage trench to attenuate any pathogens that when you have liquid overflows or liquid surges. But basically, you have large ponds and you're trying to dry the nitrogen into your sludge. Much bigger volume, much greater land requirements, and requirements for reducing the influence of your rainwater into the drying process for your, and then they've got to be graded out once it's dry and can be used as a soil conditioner. The final kind of concept is really where you try to actually concentrate your nitrogen into your effluent, which is basically, again, a sealed pond. It doesn't need to be quite so big because we're actually constantly reducing the amount of liquid coming through. But in this one, rather than having your drain at the top like the previous, you've got your drain at the bottom, and we're concentrating the nitrogen will flow through in the liquid, and you are able to actually utilize that through reed beds or through some kind of method where you want to use that nitrogen concentrated in the liquid. But then, we still need to actually deal with the pathogen. We still haven't really dealt with the pathogens. And so we need some kind of well-designed soakage area for removing the pathogens once we've removed the nitrogen. And really, in terms of simple designs for septage treatment plants, it's really about where the nutrient risks are and where you would like it to be. For packaged sewage treatment plants, and we see this is often the kind of seen as the next step on from just a septic tank, is to say, well, let's go for a packaged sewage treatment plant. Packaged sewage treatment plants, as they stand in an activated sludge process, again, don't significantly reduce your pathogens. They will give you a much lower BOD and total suspended solids, but you've still got tens of thousands of fecal coliforms per 100 mil. And so once you've been through your activated sludge package process, you basically have two options. You can then put your effluent to a soakaway, or you can actually design without a soakaway. And so looking at it from a regulatory perspective, they're really your two options. If you go for a soakaway, generally it's not, it mitigates some of the risks of failure, where the soakage area can absorb some of the risks of the failure of the plant. And if the plant fails, you will actually start, over time, you will see the soakaway start to fail. And it's an indicator of not just a problem with the soakaway, but a problem of the treatment plant. The other option is the much fancier treatment processes, where you actually need to follow up your activated sludge process with some kind of filtration and disinfection and testing regime. The reason being that if you have one of these systems that discharges to receiving waters, is that in the event of a failure, there is no indication that this system has failed. And so it does require a much higher carry much higher regulatory risks, and also much higher operation and maintenance requirements, as well as much higher testing requirements. And so while the move to packaged plants may seem to actually present a much higher performance, which it does, we do need to be cognizant of the risks associated with this move up to higher treatment options. Finally, and in the move to sewerage systems, and while network sewage definitely presents certain advantages, we need to also remember that network sewage basically starts at the point of the connection of the sewer and to the treatment plant. Prior to that, there's a whole range of behaviours that need to be managed in order to enable the treatment plant and the treatment processes to be optimised. The first of those really is minimising fats, oils and grease discharge to sewers. The discharge of fogs into your sewage system will block pipes, block pumps, block screens, and are a nightmare for your sewage treatment plant. And so there is a need to manage household and residential and commercial premises for the management of their fats, oils and grease, and the risk that pose to sewers. There's also a risk from lots of non-biodegradable waste entering sewers, and these enter through people flushing through what gets flushed, but also often during the construction processes and sometimes through a failure in the integrity of the sewers at the household level that will actually then end up blocking up your sewers. Water in sewage systems presents a massive challenge for treatment plants and for the interface between sewers and stormwater. And so educating households and educating users to reduce the amount of water and the amount of stormwater entering sewage systems really is key to optimizing sewage transfer and treatment. And finally, there are the other range of contaminants that chemical and contaminants that enter into sewers, and potentially, processes for trade waste permits and for industry to manage the contaminants that they would like to discharge into sewers is a necessary precaution to enable the management of sewage to be optimized. Still, again, lots of questions around how we optimize the on-site plants and network systems, and again, looking for collaboration and for support in addressing these ideas. Thank you. Finally, to run through the lessons is really that fecal contamination of groundwater primarily occurs through the ground, and we know that it also occurs via the surface. Septic tanks, do not significantly reduce pathogens. Most of it occurs in the soakaway. Septic tanks aren't always superior to cesspits, and in settings where you don't have access to septage trucks or low income settings, cesspits are a superior option to septic tanks, as long as we don't discharge fats into cesspits. Operating dry pit toilets in a wet pit state presents some operational challenges and can actually be addressed through the transition from a wet pit toilet in a dry state to a wet pit toilet operated as a cesspit. And finally, mechanical sewage systems are not always superior to passive systems. Mechanical systems present certain risks, and in some cases present higher risks than passive systems. Thank you very much.